Hey, hi everyone, and greetings from Optima, whichever part of the world you're in. And today we're going to have a tutorial on meeting ISO 26262 function safety targets, static and dynamic fault analysis. A quick agenda. We have two parts of the agenda today, each part followed by a short demo. In the first part, we'll have a quick introduction about us, a quick automotive function safety primer, overview of static and hardware analysis, and demo of static and hardware analysis. That ends the first part. In the second part, we look into soft errors or transient faults, challenges and design issues, calculating the soft error impact, and optimizing the soft error mechanisms and design performance due to those mechanisms, demo of it, and we'll end the session by Q&A. Optima is the next generation automotive functional safety software provider. It's founded in 2014 in Israel. We have a portfolio of advanced solutions for complex safety and security challenges. And we have revolutionary technology for high performance fault analysis. We are a well-funded organization with a core team of verification and safety experts. The core of technology, we have FIE, Optima Fault Injection Engine. It provides orders of magnitude for faster simulations than computing solutions. On top of FIE, we have Optima SE, static analysis solution, Optima HE for hardware coverage, Optima SE for software mitigation, and Optima SCC for IC security verification. And about me, I'm Sesha Sai Kumar. I have more than 25 years of experience working as Director of Application Engineering in Optima. And last 6 years, I've been working in the area of functional safety. Let's have a quick functional safety primer. Automotive electronic safety standards define functional safety as absence of unreasonable risk due to hazards caused by malfunctioning behavior of electrical and electronic systems. So this definition is given in ISO 26262 directly. And any average car today uses 300 processors and 50 plus complex electronic control circuits. These circuits take care of very critical functionalities like airbag deployment, cruise control, automotive braking, driver alertness monitoring, accident recorder, battery management, lane corrections, security system, parking assistance, lane departure warnings, regenerative braking, etc. All this critical functionality is very much required to make sure the driver and the passengers are safely inside the car. So there are many functional safety standards that are present for every industry, and ISO 26262 defines automotive safety standards. ISO 26262 fits the entire safety and verification process into a V model, right from concept phase to the product development at the system level, hardware level, software level, through the production and operation. Let's consider a typical CPU used in the automotive system. ISO 26262 defines random faults that can occur during the operation. A safety mechanism is used to correct these effects from the random faults. How will it affect? Let's say that a RAM has a fault. It can make its output permanently 0 or 1, which we call it as permanent fault or whatever. We need to have a safety mechanism to protect such kind of a permanent fault or errors. Safety mechanism in the form of ECC could do the work. The same is the case at central sensor control. You have a fault that occurs. The output is temporarily made 0 or 1, which we call it as transient fault or soft error. What could be the safety mechanism? The safety mechanism could be a hardened TMR flip-flop, right? And ISO 26262 certification requires proof that high proportion of these faults are protected. And it also defines something called ASIL, automotive safety integrity level, which we'll look into in the next slide. And ASIL D is the highest requirement, which requires 99% of the faults to be protected. So in essence, a safety mechanism is to detect and mitigate or tolerate faults, or control or avoid these failures to make sure that the entire system of the usage is in safe state. How do you determine ISO 26262 ASIL level for an equipment? It is defined as acceptable risk level for different automotive electronic applications. It depends on three main factors: severity, exposure, and controllability. Severity in the sense of if an incident occurs, how much injuries it can cause to the occupants, right, driver or passengers. No injuries, light injuries to the life-threatening injuries. So there are three categories of severity. And exposure, how probable it is for this incident to happen, or how low probable it is to happen. From low, extremely low to the high probability greater than 10%. Controllability, if this incident happens, is it very easy to control or to avoid a failure and the accident? Easy to control or uncontrollable? Based on different combinations of severity, exposure, and controllability, we have different levels of ASIL. At the highest level, we have life-threatening injuries and very high probable incident that can occur, and it's completely uncontrollable. So this makes that particular thing as ASIL level of B, right? When you are making an equipment to cater for this kind of severity level, exposure, or controllability, you should design keeping ASIL D level in mind. At the lowest level, we have no injuries, extremely low probability, easy to control, and this is very easy to manage with a simple quality management process. You can have this ASIL level for any equipment to be present in the automotive. So there are ASIL levels of the lowest, like A, B, C, D, A, or at the highest level of B also. So based on the functionality, you define the ASIL level for any equipment to be used in the automotive equipment. So what is ISO 26262 definitions of various faults? ISO 26262 defines different fault types and probabilities of failure. Let's define one by one. Safe fault. A fault that does not violate safety goals is called a safe fault. It is green, obviously, because there is no fault that creates violation of the safety goal. And single point fault. This fault that violates safety goal, but there is no safety mechanism present. So these are dangerous because fault is occurring and there is no safety mechanism present to take care of that fault. Residual fault. This also violates safety goal. There is a safety mechanism to take care of this fault, but the problem is this safety mechanism is not catering for all the faults that are occurring. So this is called residual fault. This is dangerous and not red. Multi-point faults. Alone, it cannot violate any safety goal, but in combination of another fault, it can violate the safety goal. This can further be segregated into detected, latent, and perceived faults. We'll look a little more detail in terms of flowchart in the coming slides. And fault metrics must be established for all the critical types, and these are the metrics that are defined in ISO 26262 for each ASIL level. Fit rate is defined as failure in 1 billion hours of operation. SPFM is a single point fault metric. And LFM is the latent fault metric. Let's look at ASIL D values. Fit rate should be less than 10, SPFM of greater than 99%, and LFM should be more than 90%. For more information, please have a visit to the link provided here. A closer look into the fit rate and how important it is. The fit is defined, as we defined in the last slide, as number of failures in 1 billion hours of operation. ISO 26262 requires that a range of 100 fit rate is assigned to each one. So that means 100 fit rate means one failure in 1,000 years. Oh, this is like no failure at all, right? 1,000 years, no failures. But let's have a different look at the fit rate. When a company sells 1 million cars and they are on the road, and 100 fit rate per car equals to one failure in 10 hours. This is an alarming number, right? So whenever we design something to be used in automotive, we have to reduce the fit rate to make sure the entire automotive equipment is safe. Let's again look a little closer into how we can cover the fault coverage. The fault simulations are used to measure coverage by injecting faults and simulating repeatedly, like faults are injected all over the CPUs or any control units that are used in that equipment. Traditional fault simulators built for manufacturing tests, and they're very, very slow for automotive applications. And what could be the time it takes, right? General calculation is the one gate level simulation multiplied by number of faults you have simulated. Even if you do a lot of optimizations, like reducing the fault case and things like that, but it takes many weeks further. A traditional fault simulation is an iterative process, and you need to consider these iterations in considering the overall performance. Let's have an overview of static and order analysis. Let's look at a closer zoom picture of our ICs. So this depicts transistors and then connections in between them. So there can be a fault that can occur in the connections or transistors. And for example, a wire can go touch a VDD or VSS, making it permanently 0, 1. So we can model these kind of physical deformities by way of stuck at 0 or stuck at 1. We can use many other fault models like bridging faults and other faults. But in this presentation, we'll focus more on stuck at faults. These stuck at faults can occur and the outputs of your gates. Gates are actually constraints of all your ICs, right? And this is called net-based fault modeling, where the faults are injected at output net connected to your gates, stuck at 0 or stuck at 1. Similarly, you can also have a pin-based faults that can be injected. This means that input and output pins are injected with stuck at 0, stuck at 1 for all the gates. Assume that we have multi-million gate designs these days, and the faults will be running into millions of faults at stuck at 0, stuck at 1. So you need to have a mechanism to optimize these fault lists to expedite the process of fault separation. A fault list can be optimized using fault coding, where you actually find out what are the safe faults. In OSP, Optima Safety Platform, we identified them as safe visible or safe visible. You can also do the optimization by fault collapsing. We'll see it in the next slide. This is nothing but equivalent faults can be removed from the overall simulation list, and then only simulate the required faults. And we can also do constant analysis. Look more detail into the fault collapsing. Let's look into the last stage of the AND gate, where stuck at 0 output is equivalent to the stuck at 0 input. We can use only one fault to simulate, and the rest of it we can collapse. And also similarly, an OR gate in between. This stage, the output of an OR gate and input of an OR gate stuck at 1 both are same. You can collapse one and use other things for simulation. So like this, collapse faults are counted for all the calculations, but not executed for simulation. So in this way, you're actually reducing the number of faults and thereby reducing the time it takes to simulate. So what it requires, like what is the simplified requirement of ISO 26262 for hard errors? So a semiconductor equipment or a semiconductor IC needs to have a safety mechanism that can actually detect hard errors within the budgeted time interval, right? You need to react within that fault time interval. Otherwise, the failure might take the equipment somewhere else, right? So you need to react in that budgeted time interval from the time it happens. So safety mechanism needs to be running continuously while the device is in operation. So how do you calculate the diagnostic coverage for this safety mechanism, or how do you define diagnostic coverage? So every safety mechanism needs to be able to cover not less than n% of the possible faults. This n is defined in the ISO 26262. For ASIL D, which is the highest level which we have seen in the previous slides, this n should be greater than 99%. So all the 99% possible faults in the device should be covered in order to achieve ASIL D level certification. So to put that into kind of a flow chart to understand the iterative nature of measuring the safety mechanisms coverage process. So you need to write this, run the fault simulation, and look at the results, coverage results. Are they meeting requirements? Yes, you're done. If not, you have to develop methods to improve the coverage, right? So there will be coverage faults. And fine tune the tests, go back and then simulation. There are two significant challenges available. I mean, they are present here, right? Challenge one is takes a long time to complete. As we have seen, it takes weeks to run kind of a fault simulation for a number of faults. And you also have another challenge to identify the coverage faults. they are very hard to detect. Right? So let's consider a realistic example of ethane GMAC as a device under functional safety assessment. It has inputs and it has outputs, and any fault occurs when ethane GMAC will cause a safety goal violation. So we call that as failure stroke. As we have seen, safety mechanism should detect and mitigate or tolerate faults, and it also will be able to control or avoid failures to make the whole system safe. So let's have a parallel ethane GMAC, call it a shadow, working in lockstep with the master. That means it works in the same clock or a clock delay, and the outputs are compared. And comparison outputs will give whether the fault it can be detectable or not. So we mark the outputs of compare outputs as false strokes or fault detected. No, I'm sorry. So it is like detection stroke. So here the fault is detected, and since it is fault is detected here, we are calling it as detection stroke. And the fault strokes are defined in for the master EMG, right? The output where the safety rule is violated. So let me correct myself and reiterate. So the output of the actual device is the failure stroke where the failure happens and safety rule is violated. And safety mechanism which is working in lockstep and the comparator output is marked as detection stroke. Let's see how this safety setup to be set up in the OSP, Optimal Safety Platform. So the setup is very, very simple. You consider design under safety assessment, and define certain failure scopes and define detection scopes, and run static analysis. And static analysis will form a query for the failure scope. That means all these parts of the designs will propagate to the failure scope and occur and makes it safety rule violated. And similarly, the detection scope will all these faults will appear at the detection scope. We can detect at the detection point. So there is an intersection between the detection point and the failure point, right? And there is an intersection. So let's see how the faults fall into different areas and how we segregate them. So more the user or the designer should focus more into this area because these faults are unsafe. Unsafe because they are ending up at failure scope. Or they're visible. They're not visible because they're not ending up at the detection scope. So these are the faults which don't have any safety mechanism. So that's why we are calling this as unsafe, invisible. And the designer has to make sure that there is a safety mechanism present to take care of the faults which occurs in this area. How about the green area? These are safe, invisible. They are safe because they're not ending up at the failure scope, so it doesn't cause any safety mechanism. I mean, any design failure or safety rule violation. And they are invisible because they're not appearing at the detection scope. So they are safe, invisible, and they are really safe. So that's why we mark it as green. How about the blue area? They are safe, visible. They're safe because they are not ending up at the failure scope. They're visible because they are ending up at detection scopes, right? So they are safe, visible. I mean, they don't cause any danger because they're not violating any safety goal. How about the intersection point? These faults are actually violating the safety goal by ending up at the failure scope, and these faults are also detectable, right? So these are potentially detectable faults in the design, and you need to make sure you simulate these faults to further segregate the fault list, right? So all these things we are doing to make sure that we map all these faults into ISO 26262 jargon, ISO 26262 defined faults, and then further calculate FMEDA metrics. So the safety setup, what we saw just now, can be more complex. It can be single or multiple failure modes. The safety setup can be freely mixed and matched. And it may include one failure mode with many safety mechanisms and single FM with multiple FMs with single FMs, and all FMs in the core and their safety mechanisms. So like this, you can really mix and match in Optima safety platform. And just by giving RDL gate level designs and a simple safety setup in the terms of failure strokes and detection strokes, you can do static analysis For further getting into the FMEA parameters for the fault mode sizing and different metrics, you can do static debug. As mentioned, UI faults are more to be considered, right? So designer needs to make sure that these UI faults have some safety mechanism to carry for early identification of major issues, and you have an optimized fault list. As per the definition, ASIL C and D need to have more extensive analysis of these faults. For ASIL A and B, this might be all that is required. So OSP will optimal safety platform will give you a very easy way of just reading design and setting up the safety setup, and then trying to analyze for FMEA. This is all what you might require. So how do you map these faults? What we just segregated using static analysis. The safe faults into directly into the green. This will not violate any safety goal because they're not ending up at the safety goal violation point, which we call it as fault score. Single point faults, these violate safety goal, which will end up in fault score, and they don't have any safety mechanism present in the design. Residual faults, they are residual within the design. They violate safety goal, and there is a safety mechanism present, but this safety mechanism is not covering all the faults. They are residual within the design, invisible, right? So we need to simulate further UV to make sure that these potentially detectable faults have further been segregated into residual faults. Multi-point fault detected, again UV need to be simulated. In one alone, in one fault, multi-point faults are the faults alone, they cannot violate the safety goal, but in combination they can violate the safety goal. And to make it detected or to find out whether they are detectable at the detection stores, you need to simulate the UV faults. Excuse me. And latent faults are the ones which alone cannot violate the safety goal. And you need to make sure that you are simulating SV faults to find out whether they are really latent or not. So what do? So you have to take this SV or UV faults further into simulation, and that's achieved by the hardened analysis. So what we need is a workload in the form of a VCD, a stimulus. And by giving the stimulus, we can simulate UV and SV together or UV alone. Let's see if UV alone is simulated. Some faults can get really detected because the static analysis has divided the whole fault list from the file as unsafe, visible, potentially detectable. I mean, we're not telling it's really detectable, right? So now the real workload has come, simulation has happened by our error analysis. So some faults can be detected. We call this as UVD, unsafe, visible, detected. And some faults are not detectable. They're potentially detectable by the static analysis, but when you really simulate it, they become undetectable at the detection stroke. So you need to really worry about it and make them dangerous and start analyzing more further, right? So this is called UV residual. So how do you map the entire SEA static analysis and hardened analysis resulting faults to the ISO 2626 to define FMEA metrics, right? So this is the flow chart that shows how the FMEA metrics are calculated in terms of SPFM or LFM or different other things. So SI, UV, SV are mapped into this. So I'm not getting into more details, but this is how the entire SEA and HE analysis will give us the fault segregation to map each and every fault rate. Let's deal, before getting into the challenges dealing with the transient faults or the soft errors, I would like to quickly show you a demo running the SA static analysis and I hope you guys are with me, and please feel free to let me know in case if you have any questions, but I would request you guys to take hold on for the final Q&A session, right? So this is my demo thing. So what we do is we define the complete setup in the form of ethical file. Let me walk you guys through the ethical file. So here we are just analyzing.
We're seeing the PowerPoint, not the demo.
Yeah, thank you, Vinny. And let me just share my VNC as well. Yeah, can you guys see my screen?
Yes. Yep.
Yeah, thank you. Yeah, so here, I'm sorry about it. So what I'm trying to do here is I'm trying to set up the complete thing in the form of ethical file, where I analyze the design. So the same heat and Gmac I have picked up, and I elaborate the top file. And in terms of safety setup, I need to define the detection scopes as well as failure scopes, right? So detection scopes are the ones that outputs or some signals inside the design uh, coming out of the safety mechanism, right? So here I have selected error detection of all outputs as one of the detection scope, and a couple of receiver and transmitter FIFO signals as a detection scope as part of safety mechanism. And for the false strobes, where a safety goal can be violated, I've considered all the outputs of the design as the false strobe, right? So this is where the safety setup dash default will consider all the outputs as a false strobe and then prepare the complete safety setup. So when we call safety setup for the design, it includes both detection scope as well as the false strobe. And I run static analysis. So once the static analysis is done, we can do the analysis in terms of whether the faults are UI. UI means there is no safety mechanism. Can we develop a new safety mechanism or attach this failure scope to a new safety mechanism? These things can be done. I'll show all together because of the time that we have. And then what I do is I'll pick up a VCD file and read in that. And once I read in, I have picked up some faults to be run here. Maybe some 300 faults I have picked up. And I run these picked up faults instead of running the whole fault list, right? To make sure that we have enough time. So that's simple it is to set up the design. And OSP is the command, Optima Safety Platform, where I source this design, design setup. It opens, and this Akoi triangles are familiar to you right now because we have talked about this triangles in the slides. So safety setup is read, and SA engine has run. Static analysis is finished, and static analysis has decided this is the segregation. Like there are 220 faults still which don't have safety mechanism. Like we said, any designer should go look into this first because if fault occurs, there is no safety mechanism to take care, right? So you need to go define. So assuming that you're running the first cut SEA and HE for the first time. So we don't try to fix it here in this demo, but move ahead to the hard error analysis as well. And if you look at it, there are completely safe faults of 75. There is no S3, and you have a UV of 31,000 faults. Out of it, I have picked up around 600 faults I have picked up, and we just ran it. So with this kind of a thing, what we have done is out of the 600 faults, there are 227 that are covered, right? And then 332 faults are residual. So if you remember how we mapped it, so we can directly map this UVD into the safe scenarios, and then UVR is the residual where we need to take care. They're still dangerous because if a fault occurs, they are not really visible at the detection points, but still they can violate the safety goal. So in this way, you have to really analyze all the fault flags and then try to improve the workload if needed, or try to improve the safety mechanism for some of the faults to be considered for the safety mechanism. So this is how fast we can run the static analysis as well as hard error analysis using OSP. This is a very short demo. I mean, in case if you require further details, right, please contact us after this demo. Let me get back into the PPT. So as we have seen the demo for structural analysis and the hard error analysis, and now we're going to focus some of the challenges in dealing with the transient faults or the soft errors. So what are they? Transient faults generally are termed as SEU, single event upset, or the single event transient, SET. And these are basically bit flips caused by the cosmic rays radiation from the sun. Where do they hit, or what are the different mechanisms to protect against them? Right, it can go hit the memory bits if you have a RAM block or some other block instantiated in your design. And this can be mitigated or taken care by the standard techniques like bit alignments or ECC that is provided. It can occur at the gate and get latched, but to occur exact glitch at the right point of time to be latched and further damage the downstream logic. The occurrence is very, very low probable and may not be considered by many experts. So SET, single event transient, can be neglected or it might end up in the SEU as well. So finally, it might hit the flip-flop, and there are many methods to take care of these flip-flops because the glitch gets latched and it can affect the downstream logic. So flip-flop hardening is one such method to correct such errors. And TMR, which is the triple module redundancy design with the majority order, popularly used in the design. Three flip-flops are instantiated and a majority order is designed to choose the right output of these flops. And there can be DMR with the C element as well. So this is also one of the popular techniques used to harden flip-flop from the software. You can employ at the system level as well, the same techniques like say DMR, double module redundancy, where you duplicate the actual system twice. This can actually detect a single fault, but no correction is possible. As you can see, it's instantiated twice. Your costs are increasing 2x. You can employ TMR 3x for single fault correction and dual fault detection. A module is instantiated twice, and then it is to select the correct output, and cost is increasing by 3x. TMR of TMRs, 3 implementations, and it can also protect against design bugs too. 9x of the cost. So they are very expensive designs. So you can go with a single flip-flop, and you can also do the system redundancy, but they are very expensive. Let's look at the flip-flop hardening alone, right? So you can have a unit-level lockstep mechanism where 70% of more silicon is required. You can harden all the flip-flops in the design, 30% more silicon. You can selectively do the hardening, 1 to 5%, and we'll see what the selective hardening is and how the Optima safety platform can help you do that. Using older silicon nodes, we don't go back generally because we are just advancing in the technology, or use the special red hard silicon technology, which is very, very expensive than flip-flop hardening. A closer look into the extra area and extra power for the TMR and DMR, 200% for the TMR, but the fit rate, right? So if you remember the first few slides where we talked about reducing the fit rate, and that's what is required, we got to reduce down to 0. So TMR can reduce down to 0, but the extra area of 200% or extra power of 200%, bear with it. The DMR can reduce 100%, I mean, can reduce down to 95% of the fit rate, but the extra area is increased by 100%, right? So let's look at the selective hardening in more detail. How do you harden a flip-flop selectively, right? So hardened flip-flops can eliminate transient faults and bring your fit rate close to 0. Only small portions of flip-flops are required to be hardened, not every flip-flop in the design. By way of calculating something called AVR, architectural vulnerability factor, which is calculated for each flip-flop to evaluate the fit rate. this fit rate can be optimized using iterative fault simulations while swapping the flip-flop. That means you can swap one flop with the unhardened flip-flop, calculate the fit rate, and then try to achieve the required fit rate, right? That's where you're calculating the AVR. We'll see more details into how we can calculate AVR and how fit rate can be changed. And it requires many months of compute effort or many computation resources for simultaneous analysis of AVR for all the people. And calculating these vulnerability factors is not new. A lot of the industry leaders also work. We'll see whoever is working. So AVF is simply to define AVF. It's nothing but the probability of when a transient fault occurs or bit flips happens for a flop. What is the probability it propagates to the safety goal output? Right? That's how the architecture vulnerability factor is defined. Often these flip-flops outputs might be masked because of logical masking in its signal paths. And these flip-flops, which are masked, mostly have low AVF. We can leverage these AVF calculations for all these flip-flops, which are masked also, and calculate AVF in such a way to minimize the number of flip-flops that are to be hardened. As I said, this technique is not new. A lot of industry leaders will follow this. Like one of the examples we have depicted here is Intel calculates the vulnerability, and they have an advanced flow to measure vulnerability of hardware to software errors by three vulnerability factors, which is AVR, PVR, and PVR. So we're focusing more on the architecture vulnerability factor in this presentation. And if you want to see more details, you can look at Intel presentation that I think paper. So how do we calculate a reliable AVF? Because as we have seen, we have to calculate AVF for the flops which are instantiated in the whole design, and it takes a lot of time. So multiple SE simulations are to be performed for each flop. What it means is each flop will be injected with a software error at different time cycles in the simulation. And Optima recommends 50 to 100 faults per flop in this simulation time frame. So each fault in the simulation can end with a propagated fault. That means a fault propagated to a safety critical node, or it is dissipated. That means it disappeared from the simulation in that simulation time cycle. Or it can be end of a trace where the simulation has stopped simulation and without any results of one of these propagated or dissipated. So AVF can be defined as a number of propagated faults over total fault simulations executed. So how we use that, right? So suppose if you are calculating the fit rate without any AVF calculations in the chip, the fit rate is simply the number of flip-flops instantiated and the fit rate of unhardened flip-flop. So this gives the overall fit rate of the chip. And if you are really meeting the requirements, yes, you don't need to go with the AVF for the calculations. You can just stop here. If you're not meeting, right? So how do you accurately calculate the fit rate chip? Fit rate of the chip. So you can calculate the AVF, but you're not at started the hardening or replacing the flops with the hardened flip flops. So this is simple calculation by just calculating AVF for each flip flop. So fit rate of the chip will be the AVF for each flip flop and fit rate of the unhardened. So now we calculated. Earlier it was calculated with n directly the number of flip flops instantiated, but right now we are calculating with the AVF factor, right? So now the fit rate unhardened has reduced further, and you're just adding all the AVF and multiplied by fit rate of that particular flip flop and adding up for the instantiations. So this can be a reasonable calculation, or accurate calculation, and if you're meeting the requirement, it's very good. So in this way, AVF calculation has helped us in arriving at the accurate fit rate of the chip. But what if you have not achieved the required fit rate? So then you have to go selectively harden the flip-flops. So at that time, let's assume that you have hardened M flip-flops. So now the calculation will be more accurate. So you can calculate hardened flip-flops fit rate, and you can also calculate unhardened flip-flops fit rate. So for the hardened flip-flop, obviously the fit rate will be close to zero, and this term is very, very close to zero. And this term, anyway, AVF is low and unhardened devices or flip-flops fit rate will be multiplied with the AVF, which is low in number. So this second term is also going to be low. So overall, you're going to lower the fit rate of the chip by hardening it and also calculating the AVF of it. Right. So this is more accurate calculations of the fit rate, and then you can achieve the fit rate requirement by way of selective hardening. So calculating AVF takes many compute resources, and it involves performing fault simulation on all the flops, and each flops to be fault simulated 50 to 100 times, as we said in the last slide, that Optima recommends 50 to 100 faults to be injected in the time frame. Historically, and this is a very lengthy process, takes many compute resources, as mentioned. So we need a new approach to fault simulation and also a platform to manage these large number of faults. So to put it in perspective, how iterative it is, you have to measure the fit rate of using AVF calculation. Did you meet the fit rate requirement? If not, go perform the hardening on the selected flip-flops. You calculate post-hardening fit rate. Did you meet it? Otherwise, you come back and harden some more flip-flops, calculate hardening fit rate, and then do this iterative process. So in most cases, what we observe is hardening less than 5% of the flops will get you closer to the zero fit rate to meet ASIL D requirements, right? So with minimal silicon cost or power consumption. So in essence, what you need for the accurate software analysis and AVF calculations, managing these whole simulations is an ultra-fast simulator and a dedicated platform, right? Dedicated integrated application. Ultra-fast simulator because you need to accurately calculate AVF and it requires at least 50 fault simulations as we have seen. Multiply this by number of flops and millions of fault simulations, and regular simulators are very difficult to cater less. And you need a platform because multiple simulations are running. You need a management to collect the results per unit basis, and you have to calculate AVF for each flip-flop and deal with all the different failures, cache reserves, etc. Right. So this is where you can look into the OSD and try to optimize the ASIL analysis. Right. So this is what I have, and thank you for listening to us. And any further information, please contact info@optima.com. Actually, we have a video of SC we played. How do we do that? Jamil, do you have any suggestion?
Yeah, I think now we can take questions. Anything
So
that you have?
Any questions?
So we have time. Don't worry. You can ask any question you want.
Yeah, maybe I try to finish within time. So please go ahead. I'm trying to look for the demo video.
Okay.
Hello, can you hear me? Sylvia speaking.
Yes, let me take question while he gets the video up.
Yes, okay. In the beginning, you set a picture where you have the comparison between two simulations, and you talk about some shadow part. I can't remember exactly. And my question is now: is it can I understand it like a model, like a behavior model, or if you like, yeah, exactly, or like we have it for registers, a register model? How is this?
Yeah, this is not about comparing two simulations. Actually, putting two hardware pieces. Sasha, can you share the PowerPoint? Not
oh, sorry, yeah.
So it's about this is, in this case, lockstep is very common methodology in functional safety.
Mm-hmm.
Case, the hardware designer is actually putting two CPUs or two.
Okay. Mm-hmm.
And two hardware are running in parallel all the time and comparing results to know if we have a failure or not.
Okay, this I know. Okay, I thought maybe it's from simulation only. Okay.
Yeah. May I know, Sylvia, where are you from? I mean, which company you are from?
So, does this answer your question?
Yes, thanks.
Okay.
Thank you.
Any other question while Sasha is getting up the other part?
Yeah, sorry, I didn't download it because we just presented to them, right? So I didn't download the video.
Maybe you can use the full video that we sent to DVCon.
Yeah, I mean, it's online actually. So, give me a second. I mean, meanwhile, we can take some more questions if somebody has on functional safety or on Optima safety platform.
So by the way, if anybody registered for this conference and or if you register after for this tutorial, we can send you our giveaway, which is a camera cover for the laptop. So you can do like this, and now nobody sees your camera. We'll mail it to you to your home or work.
So can you guys hear my audio as well, or I'm not sure?
Yeah. Can you play it? We don't.
I'm actually playing. I'm not sure if you.
No, maybe you can.
Hello, this is the moderator. I will share the video if you need me to share it, and we'll put it in about 40 minutes.
Yeah, so you can play from 34 minutes, 34th minute.
34.
34th minute, yes.
Okay, I will do that.
Sure, thank you. Yeah, meanwhile, we can take questions then.
Not this one. No, this is different company. So the demo that hopefully we'll show in a second is for the software or solution. The main concept here is that we do fault simulation on many flops
34th minute, yeah.
to calculate the AVF so that you can do selective hardening to decide which flops need hardening and which don't. Okay, let's see if it works. Yes, that's the point.
Is there sound coming? Or no?
Maybe you just play it and maybe Sasha can talk over it.
AVF based fit rate, you need a fast simulator as well as a dedicated platform. Thank you. For any queries, please contact info@optimada.com. Let's look at SE demo. Thank you. Load the design using Tickle, and OSP safety platform would have already marked some of the nets as critical. You can browse through the database and mark yourself some nets critical. This can be done using GUI or using Tickle interface. Once the nets are marked, you can run the prep engine, and this will actually do the COI analysis and prepare the database for all the critical flip-flops. In this run, we're going to run 20 faults per flop. The Optima safety platform can perform soft error injection and also create the simulation VCDs. This can be used only for debugging, otherwise there is no analysis needed graphically. Now you can see the third row, which is the AVF, is populated with some numbers. This will indicate the vulnerability factor for the flops, and overall the top 5% of the flops are selected for the hardening. In this run, we're going to see only 3.5% of the flops are selected in the whole design. Yeah, the run is finished, and you can see only around 3.5% of the flops are selected for the hardening. In this way, Optima safety platform provides an easy way to analyze the soft error for various flops and to recognize what are the vulnerability factors for different flops and select the top 5% of the flops for the hardening. Thank you. For any queries, please contact info@optimada.com.
Yeah, and that ends our session. Any more questions, please let us know. Jamil and myself, Jamil is the CEO of Optima. Jamil and myself are there.
Yeah, so we can take the question either just saying it, or if you want to type it on the chat group chat.
That's also fine.